In this video, we'll be taking a look at integral equations. Integral equations are those in which the unknown function, such as y of u, appears inside an integral sign. Even though it may be written with respect to another variable like u, it is still the same function y we are solving for. And that's what makes it an integral equation. Now, for such cases where the function appears under an integral, we will be using the convolution theorem to solve this equation. Here, we are asked to find the value of y of t, but it appears in the form of y of u. To proceed, we will rewrite this expression using the convolution form. According to the convolution theorem, the y of t asterisk g of t was written like this. Here, if you compare it, the y of u is written the way it is, and sine of t minus u is written as g of t minus u. So if we are going in reverse, we'll be replacing y of u with y of t and g of t minus u with g of t, placing this asterisk symbol. Let's do that. When we took the Laplace inverse of f of s and g of s, we wrote it as f of t asterisk g of t. So when we go in reverse order, we'll be taking the Laplace transform on both sides of the equation, like this and this. This and this are going to cancel out, leaving us with only f of s dot g of s. Instead of writing y of t asterisk sine of t in above equation, we are going to take the Laplace transform on both sides of the equations. And we'll be writing it as f of s dot g of s. The f of s and g of s are the individual transforms of the f of t and g of t individually. To clear things up, we just found that the Laplace of f of t asterisk g of t is equal to dot product of f of s and g of s, where f of t is y of t and g of t is sine of t. Now you're going to solve this equation by taking the Laplace transform on both sides of this equation. So let's do that. Now we are going to find the Laplace of y of t and sine of t individually. So let's do that. Now we can see that y of s is common here and here. So we'll be taking it towards the left-hand side of the equation and simplifying it. Taking this to the right-hand side now. Since we were trying to find y of t, we are going to be taking the inverse Laplace transform on both sides of this equation. This is going to be our final answer. Let's solve this question and let's find the value of f of t. The one thing you can notice in this question is that this is the integral equation, but instead of variable u being used here, we have a variable tau. So this is f of tau, and this is another function which you'll be representing with g, t minus tau. Now, if you're going to be applying the convolution theorem here, then we know that the g of t asterisk f of t is equal to integral from 0 to t g of t minus tau f of tau, where g of t minus tau is this one, and f of tau is this one. So let's write it in this form, g of t asterisk f of t. This means that we'll be writing t asterisk f of t. So let's rewrite this equation. Taking the Laplace transform on both sides of this equation, and then applying the convolution theorem onto this. Now we're going to find the Laplace transform of t and f of t individually, and then write them together. Taking f of s common, taking this to the right-hand side. This s and this s is going to cancel out, leaving s power 1 in the numerator. So we get the form s divided by s squared plus 1, which is equal to sine at. This is going to be our final answer once we take the Laplace inverse.